All right, so we have this disk with rotational inertia I1, rotates with angular speed omega naught. Second disk with rotational inertia I2, not rotating drops on the first cylinder shown above. Because the surfaces are rough, the two cylinders will spin with the same angular speed. Derive an expression for omega f in terms of I1, I2. Now, this is a collision again. But again, the idea is if you make the system both objects, there's no external torque. Right? So the torque over time is equal to 0, which implies the change in angular momentum is 0. That means the initial angular momentum here and the final angular momentum here are the same. Well, this one is the angular momentum of everything in our systems. That's I1 times omega naught. This thing is not spinning, so it has no angular speed. Right? It's I2 times 0. You could write it as I2 times 0. And then the angular momentum here is I1 and I2 are now together, and they're moving with the same angular speed omega f. Okay, so it would just be I1 omega naught equals I1 plus I2 omega f. And you can solve for omega f. It's I1 omega naught over I1 plus I2. Okay. Calculate the ratio of the final initial and kinetic energy of the system containing two disks where I1 equals 3I2. Your answer should just be a number. Okay, so look at this initial kinetic energy. Right? This thing doesn't have any kinetic energy or no rotational kinetic energy. It's just this thing has rotational kinetic energy. So it's 1/2 I1 omega naught squared. Now at the end, they're both moving together, I1 plus I2 times omega f squared. But now they're telling you I1 is 3I2, so this is 1/2. Replace I1 with 3I2, so this is 4I2 times omega f squared, but we actually found what omega f was, right? It's I1 omega naught over I1 plus I2, which again, I1 plus I2 is 4I2, right? So then this becomes 1/2 times 4I2 times I1 squared omega naught squared over 16I2 squared. And then one of those I2s cancel. That becomes 4. This becomes 1/8 I1 squared omega naught squared over I2. And then we want the ratio of the final to the initial kinetic energy. So we want to do this thing over this thing here. Now, I want to get rid of this I2 to get rid of a number because then these might cancel. So I2, we remember, look here, is 1/3 I1. Right? And that way I can plug that into here. So this is 1/8 I1 squared omega naught squared over 1/3 I1. So one of these I1s cancel. And this becomes 3/8 I1 omega naught squared. So now we're going to do the ratio, kinetic energy final to the initial kinetic energy. And that's going to be 3/8 I1 omega naught squared divided by 1/2 I1 omega naught squared. And those will cancel. And it'll be 3/8 times 2 over 1, which is 3/4.